welcome back to Lesson 13 class notes. By now you should have already worked on the Lesson 13 worksheet and you should have written that completely in with your lab partners. And we're going to look at the notes now at the end of the lesson. So when we're looking at these notes, we want to remember that we just did an activity looking at numbers of neutrons. So that's really what we're focusing on here because we're looking at isotopes. So atoms of the same element that have a different number of neutrons are called isotopes. The percent of each isotope of an element that occurs in nature is called the natural percent abundance of the isotope. That means that the one that is the most abundant in nature is going to be closest to the average atomic mass that you see on your periodic table. Chemists use a special notation to symbolize an isotope. We have to find some way that if we're going to write that we have boron, but we have two different forms of boron with two different masses, remember they have the same number of protons but different numbers of neutrons, we have to have a way to talk about that and write the symbol. The capital B for boron will not be enough. So one way to refer to the isotopes is to use their mass numbers. This screen shows you what it would look like if we were going to write the boron symbol for both different isotopes. We have boron with a mass of 10, 5 protons, and 5 neutrons. That's what gives us our mass of 10. And then we have an isotope of boron that has 5 protons and 6 neutrons. 11 minus 5 is 6. So its mass is 11. So we call this one boron 10. We call this one boron 11. So it's pretty simple. Now, this is a picture of 100 atoms of neons. It's really just a model of it. But what they did in this model is they kind of color-coded. If we had a random sample of 100 atoms of neon, only one of them would be neon 21. It has 11 neutrons. 9 of them, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them would be neon 22. It has 12 neutrons. And neon 20 would represent the other 90 little atoms in here, and neon 20 has 10 neutrons. So if we were going to come up with an average here, we'd have to say that the most abundant form of neon in nature is neon 20. So if we look at the periodic table, we would expect that the average atomic mass is very close to neon 20. So look at your periodic table. Neon is element 10. You can see that its average atomic mass is 20.18. And so you would expect it to be a little over 20 because we have 22 and 21, masses of 22 and 21. So we would expect it to be greater than 20 when we take an average, but we would expect the average to be very, very close because 90% of neon atoms in nature are atoms neon of 20. The average atomic mass of an element is a weighted average of the masses of the isotopes in a sample of the element. So if you remember looking at the worksheet we did, and I set that equation up for you at the bottom, that's how you calculate a weighted average. You multiply it times the percent abundance of it in nature. So that's something when I get back that we'll practice the math of that. And once you have the equation and you set things up in the equation in the correct way, it's pretty easy. The most common isotope of an element frequently has a mass that is close to the average atomic mass given in the periodic table. So quickly look on your periodic table for element number 9. That's fluorine. So fluorine has an average atomic mass of 19.00. So you can make the guess that the most abundant form of fluorine out there is fluorine 19. Okay, go find cobalt. Cobalt is number 27, element 27. Cobalt has an average atomic mass of 58.93. That means that the majority of cobalt in nature is cobalt 59, because we're going to take that 58.93 and round it. But we know that even though most of it's cobalt 59, there must be something less than that, like a cobalt 58 or cobalt 57, for the average to turn out to be 58.93. Let me go back one. The most common isotope of an element frequently has a mass that's close to the average atomic mass given in the periodic table, and that's what I just demonstrated. So here's our wrap up. How can atoms of the same element be different? Well, they're going to be different when you're looking at the number of neutrons. Protons cannot be the same, or protons have to be the same if it's the same element. If you change the number of protons, you have a different element. So if we have atoms of the same element and they're neutral, they're going to have the same number of protons and the same number of electrons. They'll have different numbers of neutrons. Isotopes of an element have the same number of protons and electrons, but different numbers of neutrons. The average atomic mass of an element listed in the periodic table is the weighted average mass of the naturally occurring isotope of that element, and we weight it by the percent of that particular element out there. Isotopes are referred to by their mass numbers, as in carbon 12. Okay, here's a check-in to see how you're doing. So it says nitrogen has 2 naturally occurring isotopes. Predict the number of neutrons in the 2 isotopes of nitrogen. So find nitrogen on your periodic table, and there's nitrogen 14, and its average atomic mass is 14.07. So we round that to 14, and we can automatically find one of the isotopes. So it'll be the one that has 7 neutrons. So that'll be nitrogen 14. However, there must be another nitrogen with a mass out there. And so since nitrogen is 14.01, that means that there must be a nitrogen 15 out there. And it must be a really small amount or percent of it out there for nitrogen to be 14.01. There must be much more of the nitrogen 14 than 15. So that answers our question. Which isotope do you predict to be more abundant? Nitrogen 14, and we know that because the periodic table has an average mass of 14.01, and the average will always be very, very close to the most abundant form that's out there.